Okay, in this video, which is going to be the last last installment on the videos on residues, we're going to do some more examples of how to find residues of complex functions. So here are the functions we're going to find the residues of, and here are the formulas that we are going to be using. So in the first one, we've got f of z equals to 32 over z to the power 4 plus 16. So the first thing here we need to do is to find the singularities, which will happen when z to the power 4 plus 16 is equal to 0. So here z to the power 4 is going to be negative 16, which we can write as 16 then exponential of I pi plus 2 pi ki, where k is an integer. Then z is going to be the fourth root of 16, then exponential of I pi plus 2 I pi k over 4. K here is going from 0, 1, 2, and then 3. So this is saying that z, there's going to be 4 values. The first one is going to be 2 to the I pi on 4. This one is in the first quadrant. Then 2 to the 3 I pi on 4. Then 2 to the negative 3 I pi on 4. Then 2 e to the negative I pi on 4. So they are located a bit like this on the Argand diagram, circle of radius 2. Then, so what it means is that z to the power 4 plus 16 we can write as z minus 2e to the I pi on 4, z minus 2e to the minus I pi on 4 times z minus 2e to the 3i pi on 4, and the last one z 2 minus 3i pi on 4. And of course, so what this means is that each of these they are going to be simple poles. So these are going to be simple poles because they're simple roots of the denominator. So that means we can use this last formula here. So the residue, if we start with the first one at z equals to 2e to the I pi on 4, so it's going to be 32. Then we do derivative of the denominator, so that's going to be 4z cubed. Then we plug in 2e to the I pi on 4. So 32 over 4 is 8. Going to be 8 over 2e to the I pi on 4 cubed. So that's going to be 8. This is going to be 3i pi on 4. So that's just going to be 1 over 3i pi on 4, which is the same as e to the minus 3i pi on 4. Well, minus 3i pi on 4 is just this angle here. So this one is going to be in the third quadrant. So this is going to be minus 1 over root 2. 1 plus I. So you can actually confirm. So this thing is the same as cosine 3 pi on 4 minus I sine 3 pi on 4. So that's the first one, and then the rest of them are going to go in exactly the same manner. It's just it's going to be different numbers. So here, if we simply plug in z equals to 2e to the 3I pi on 4, so this time it's going to be 8 over 2e to the 3I pi on 4 cubed. So it's going to be 8 over 8e to the 9I pi on 4. So this is going to be 1 over e to the 9I pi on 4. However, e to the 9I pi on 4 we can write as 1 over e to the 2I pi times e to the I pi on 4, because 9 pi on 4 is 2 and a quarter. So, but e to the I pi, e to the 2I pi is 1. So this thing is just 1 over e to the I pi on 4. So it's e to the minus I pi on 4, which is in the fourth quadrant. So this one is 1 over root 2 into 1 minus I. Then the third one is 2e to the minus 3I pi on 4. So just in case you're wondering, so this is the one for which k here is 2. So that's going to be 5 pi over 4 if you are reaching that angle along this way. It's 5 pi over 4, but this way it's minus 3I pi on 4, which is what we're using here. Either of them is going to be good enough. That means, so when we work out the residue, I am using the minus 3I pi on 4. So we simply substitute this here for all of them. So it's going to be 8 over 2e to the minus 3I pi on 4 cubed. So 8 here, 8 here, minus 9I pi on 4. This is now going to be similar to what happened here, because this is 1 over e to the minus 2I pi e to the minus I pi on 4. But e to the minus 2I pi is 1. So this time, this thing is going to give us e to the I pi on 4, which is the one in the first quadrant. So this is what we are going to get. Okay, and then for the last one, so residue of f when z is 2e to the minus I pi on 4. So it's going to be 8 2e to the minus I pi on 4 cubed. So there's going to be 8 over 8e to the minus 3I pi on 4. This is going to be 1 over e to the minus 3I pi on 4, which is the same as e to the 3I pi on 4. So that's in the second quadrant. going to be 1 over 2 minus 1 plus I. So that's going to be all the 4 residues of this function at each of the singular points. If we go to B, we've got ZE to the minus 2I over Z. Just make sure. Yes. So this one, you can see that this term here is going to have a problem when Z is 0. So Z is 0 is a singularity, but is it a simple pole? Is it a double pole? Is it a removable singularity? So since this one is not a rational function like polynomial over another polynomial, that's not so straightforward to see. So whenever that happens, we have to rely on working out a Lorentz series expansion of this. And so for that, we're simply going to use the Taylor series expansion of E around the origin. So we're going to have Z into 1 minus 2I over Z, and then negative 2I over Z squared. This one is going to be times 1/2. So basically what we're going to be using, just maybe before we do this, so basically what we're going to be using is the result E to the U is 1 plus U squared over 2 factorial, U cubed over 3 factorial, etc. So that means our f of Z is going to be Z into 1 plus negative 2I over Z plus 1/2 negative 2I over Z squared plus 1 over 3 factorial negative 2I over Z cubed, etc. If we simplify these, we're going to have 1 minus 2I over Z. Then here negative 2I squared is negative 4. So this is going to be minus 4 over 2Z squared. And then negative 2I over negative 2I cubed. So negative 2 times negative 2I times negative 2I. So the negatives, so these two will give a positive. So this is going to be negative 8I cubed, but I cubed is negative I. So that means this is going to be plus 8I over 6 times Z cubed. So that's going to be that term. And then if we multiply through by the Z, that's going to be Z minus 2I minus 4 over, it's just going to be 2 over Z, and then plus, if we multiply this thing by Z, it's going to be 8I over 6Z squared, etc. So the principal part of this, you can see here that the negative powers are going to keep going. So this is telling us that Z equals to 0 is an essential singularity. And then from the Lorentz series, we can simply read the residue because the residue of f of z is simply going to be the coefficient of 1 over z in this case. So it's simply going to be -2. All right, so at this point, we'd like you to have a go at the last two exercises. Just pause the video and have a go at this, and then when you continue the video, then you can compare with our solutions. All right, we're now going to scroll down to our solutions for C and D. We would like to thank you for visiting our channel and watching this video. We would like to we hope that the channel or the video is useful. Please do, of course, subscribe to support us so that we can make more videos like this one. And if you've got any questions, please feel free to post them on the comment section. Okay, so for this one, the function is going to be singular when 1 minus z cubed is 1. So that means z cubed is equals to 1. 1 we can write in exponential form like this, because the argument is 0 and then plus multiples of 2 I pi. When you take the cube root, this is what we're going to get. For k is 0, is going to give us 1 back. For k is 1, it gives us that. For k is 2, it gives us that. These are located like that. So this is 1, this is e to the 2i pi on 3, and this is e to the 4i pi on 3. So notice, of course, that this one, if we like, we could write as minus 2i pi on 3. Then if we differentiate the denominator and plug in z equals 1, the first residue is equals to 1. For the second one, we plug in this, which is going to give us e to the 4i pi on 3. If we bring it to the numerator, it's negative 4i pi on 3, which is simply this angle here. So we're in the second quadrant. So in the form a plus ib, it's going to look like that. Do the same thing with this one. The denominator gives us 8 e to the 8i pi on 3. Now 8 on 3 is 2 and 2/3. So this one is 1. And then this one, if we bring it in the numerator, it looks like that. And so it's going to be that in terms of a plus ib. For this one, D, the first issue is whether this is a pole of order 4 or not. And because sine is also 0 at 0, then it becomes safe for us to expand this in a Lorentz series. So that's going to tell us what type of a pole it is. And when we do that, we find that it's actually a pole of order 3. So it means even though it looks like a root of multiplicity 4, it's actually a root of multiplicity 3, root of the denominator. So 0 is a pole of order 3. And then from the Lorentz series, we can simply read off the residue, which is minus 4 on 3. Now, just in case we had decided to go the route of finding it using the formula, so we're just going to show you how involving it was going to get. So that's the first step, that's the second step. Then we need to do the two derivatives here. There is the first order derivative. Then for the second order derivative, this is what the numerator is going to look like. Now notice here that so this term cancels out with that term, so then we're going to end up having these three terms in the numerator. All of them involve a multiple of z, so we divide by z, So that is what happens when we differentiate for the second time. So then plugging it into the definition, so we're looking for the limit of this as z goes to 0. And then again, if we plug in z is 0, then we get 0 over 0. So we can use L'Hopital's. So with L'Hopital's, we differentiate this separately and this separately. The derivative of this one is here, from which you can see that this cancels out and this cancels out. So we just have negative 8z squared over cosine 2z. And then, of course, derivative of z cubed is 3z squared. So that's what we're going to have there. And then z squared cancels out. And then at this point, you can plug in z equals to 0. And again, it gives the same negative 3, negative 4 and 3. But you can see how much work this one has demanded. All right. So that just shows you that you always need to have your Lorentz series ready to use in case one of these the formulas are working out and giving you complicated expressions.